Okay, so we're heading towards the close of this chapter. First, we're going to talk about limits in infinity, and then we're going to spend two sections on sequences. Okay, so sequences, it's sort of doing the same thing that we did before, but for when right now we're talking about a function as you approach some value, right? The limit of a function as you approach some value, right? A sequence is basically like a function, but not continuous, right? It's a bunch of discrete values, okay? And so we'll basically do the same thing over, but for these discrete functions rather than for the continuous functions. Okay. Yeah, I'm not sure. The amount of work we're going to put into sequences is, I'm not sure if it's sort of worth the bang you get for it. You're going to put in a lot of bucks, but the bang you get out of it, I'm not sure how if it's worth it. But we're going to do it anyway. So today, 2.4, limits and infinity. And this is basically making a little bit more precise the notion of asymptotes that you've probably encountered before. Okay, so here's let me sort of give you the motivation for this. If you have a function like this, if you look at limit of sine 1 over x as x approaches 0, limit of sine 1 over x as x approaches 0. Well, that's a really crazy function, right? As x tends towards 0, 1 over x tends towards infinity, right? So it zooms off to infinity, right? And so basically you're squashing in the infinite behavior of the sine into here. So it looks something like this, right? As x tends towards 0, 1 of x goes to infinity, and the sine of 1 over x is going to oscillate rapidly. Okay? Yeah, same thing. Or the flip on the other side. Okay. So for this sort of thing, we say there is no limit as x goes to 0. Okay. There's no limit as x goes to 0. But for something like this, the limit of 1 over x squared as x goes to 0, well, you've got 1 over x squared, something like this, right? Okay, and so on both sides, the function is not really going. I mean, it's heading off, without limit, but it's not wild like this. Okay, and so we distinguish. Up until now, we've said this doesn't have a limit, this doesn't have a limit, but in fact, we say that we have a term for this sort of limit, and it's that the limit is infinite. That the limit is infinite. Okay, so we distinguish between these different sort of failures of finite limits. This we call an infinite limit. This still doesn't have a limit. So the idea is that the function increases without bound as x tends to c, right? So the limit is infinity. The limit is infinity. So that's roughly what. Now the precise definition is this one. Okay. We say the limit is infinity plus infinity if given any height m, given any height, there's an interval minus delta, c plus delta. Such that f of x is bigger than m for all x in c minus delta, c plus delta, excluding the center. So we don't care about c.
What's the little
So
diagonal line?
excluding c itself. We don't care what happens with c itself. Here, it's not even defined at 0. Okay. And let me give you the. I'm pretty sure you're not going to like it, but I'll give you the notation, the concise way of writing it. People write it this, for all m in R, there exists a delta, so that if x minus c is less than delta and greater than 0, then f of x is bigger than m. So that's the concise, that's the mathematical notation way of writing the above. Okay. Given any height, there's a distance, so that if you're within that distance of c, but not at c itself, if you're within delta of c, if the distance of x to c is less than delta but greater than 0, so that you're not at the center itself, then the value is bigger than m. Yeah, okay.
What's the m in that?
So let me show you. In the picture here, we say that the limit is infinite. Well, let me hold on. Looks like people are still writing. Okay, here we go. So, right, here's something, and this is something that you would like to say, the limit is infinite, right? As x goes to 0, this is 1 over x squared. As x goes to 0, the limit is infinite, right? That's your intuition. Right? So, how does this match up with the definition? The definition says, given any height, so let's choose a height. Given any height m, there is an interval around 0 in which m is exceeded, right? And indeed, look, if I choose this interval, all my values are bigger than m, right? And if somebody chose this m, you'd say, well, I'm going to choose a slightly smaller interval, and then all my values exceed your m, right? So given any bar, you can find a place around C where everybody is over the bar. Okay, and if you can do that for every bar, then we say that the function tends towards infinity, that the limit is infinity. Okay, so what does it mean to be infinite? It means that given any bar, you can find a place where all the values exceed the bar, right? No matter what bar you choose. Okay, and so that's what this is saying. Right. Given any height, there's a distance to c, so that if you're within that distance of c, but not at c itself, then all your outputs jump over the bar, right? Right. If you're in the punctured neighborhood, then all your outputs jump over the bar. Right. So, for example, if I said I'd like all your values to be greater than 1, what interval would you choose? This is the function 1 over x squared, and I'd say, can you guarantee me that all your values stay bigger than 1? How close to 0 do you have to be to ensure that your values jump over 1? Could I take 10? Could I use 10? No, that's not going to work because my value would be 1 over 100. Right? How close do I have to be to 0? Victor?
1.
1. Right? As long as I'm between -1 and 1, well, my values are all going to be bigger than 1. Okay? Is that clear? Right. Suppose I said, I'd like everybody to stay above 10. What interval are you going to choose? Take 30 seconds and figure it out. 10 seconds. Or maybe I should use 100, that's better. How close to 0 do you have to be? 0.1. Yeah, as long as you're within 1/10 of 0, then all your outputs are going to be bigger than 100, right? Because at 1/10, what's 1 over x squared? Well, it's going to be 1 over 1/10 squared. That's 100, right? So as long as you stay within 1/10 of c, then all your values exceeded, okay? Et cetera, et cetera. You see that for any height I choose, you can find a place where all the values exceeded, right? And so the limit is infinite. Okay, everyone all right? All right. Any questions? Okay. So this is what you didn't know it, but this is what you were doing when you talked about asymptotes back in wherever you encountered asymptotes. So if the limit is infinity as x approaches c, and it could be just from the left side or from the right side, or it could be from both sides. We say x equals c is a vertical asymptote of f. Okay, so x equals 0 is a vertical asymptote of 1 over x squared, right? X equals 0 is a vertical asymptote of 1 over x squared, right? In other words, the limit of 1 over x squared as x approaches 0 is infinite, right? However you want to say it. The limit is infinite. Oh, and I should say it could be plus or minus infinity. Right. It could be, if it's negative, if you're heading to negative infinity, that's also considered a vertical asymptote. Right. Or if you're going to negative infinity on one side and positive infinity on the other side, that's also considered a vertical asymptote. That's also called a vertical asymptote. Let me do, let's do an example. Okay, so a simple one, right? If I have 1 over x minus 4, where's the vertical asymptote? At 4, right? Right, 1, 2, 3, 4. Right? This looks like 1 over x, but shifted over four steps, right? Right? And so you know that 1 over x has a vertical asymptote at 0. 1 over x minus 4 is going to have a vertical asymptote at 4. Right? Okay. Right. What about if I have something like this? Where are the vertical asymptotes? 1 and 4, right? 1 and 4. 1 and 4. Kind of vertical asymptotes. Right? So near 1, near x equals 1, the function, it's basically like 1 over x minus 1 times negative 3. Right? Because when x is close to 1, right, when x is close to 1, this x minus 4 is pretty close to negative 3. Right? So the function looks like 1 over x shifted by 1, but multiplied by negative 3. Right? Multiplied by negative 3, so it goes up here and down here. Right? Since it's multiplied by a negative number, you flip the graph. Right? And near 4, near x equals 4, this thing looks basically like 1 over 3 x minus 4. So it looks like the 1 over x graph multiplied by a third and shifted over by 4. So it's going to go down and up. Right? Okay. Here's a problem for you to try. What about x squared over x squared x plus 1? Where are its asymptotes, its vertical asymptotes? So take a minute and see if you can see what you can figure out about it. Feel free to talk to each other. Okay, who would like to say something? Anybody want to say anything? Other.
Yeah, there's one and x equals negative 1.
1 and x equals negative 1? Okay. So at x equals negative 1, the thing looks like what? Well, when x is near negative 1, well, this cancels out, and you basically you just get this. Right? So it looks like 1 over x, but shifted over. Right. And what about anywhere else? 0. Kimaya?
0.
0? Let's look at the limit as x goes to 0 of this thing. What's the limit? Like the limit, we want the limit to be infinite. Is it infinite? As we approach 0.
How would you solve that? Oh, that's right. I know it's not.
That's right. In fact, the limit is going to be 1. Right? Because as x approaches 0, right? As x approaches 0, x is not equal to 0. Right? So it's okay to cancel off. It's okay to cancel off these things.
Yeah.
Right? And as x goes to 0, you get 1.
Then what does this graph look like at 0?
1. Looks like 1.
But can't you not, but if you plug in 0, you get
Oh, actually, so I'm sorry. This function is not defined there. It's not defined there.
a little open circle.
You have an open circle, but the function approaches 1.
Okay.
Approaches 1. Like the limit is 1, but the value of the function there is not undefined.
Why is it undefined?
Because when you plug in a 0 here, you get 0 over 0 times 1. 0 over 0, which doesn't make sense. Yeah, Victor.
What do you call those holes?
This, we had a term for it. It was a removable discontinuity. If you filled it in, you could fill it in, and then it would be continuous there, right? Because the limit is 1. If we defined a new function, right? If we defined a new function, that is just like your old function, but takes on the value 1 at 0, then this guy would be continuous at 0, right? Because the limit is the value of the function there, right? So it has a removable discontinuity. Any other questions?
So negative 1 is the only asymptote, right?
Negative 1 is the only asymptote for this one. Yeah, it was a trick. Now, we talked about vertical asymptotes. We also want to talk about horizontal asymptotes. So that is this sort of thing, right? You have some function, and it's approaching a line, right? So there's some line, right? There's some line y equals L, and your function gets arbitrarily close to that line, right? The difference, your function gets arbitrarily close to that line. That's the sort of hand-wavy idea of vertical asymptote. Again, we have a more mathematical way of describing it, which is called the limit as x goes to infinity. So as x goes to infinity, the values of your function go to L. Okay, that's how we. That's the thing. That's the concept that corresponds to this picture. Okay. And the way you define it is like this. We say the limit of f of x is L as x approaches infinity if given any epsilon, there is a point n past which f of x minus L is less than epsilon. Let me use a more familiar looking function. Let's just look at f of x is say 1 over x. Right, f of x is 1 over x. As x goes to infinity, what's the limit? What's the limit? It's going to be 0, right? So people are still waiting, so I'm going to just hang out here. I should do an exercise or something. Last summer, I tore a disc in my spine, so I'm actually should be doing exercise constantly. Or if you see me sort of straightening out like this, it's not because I'm arrogant, it's because I'm straight. The doctor told me to. I felt like sort of regretful that he said, you have to stand like this, because then you look like a jerk, right? Right, but so that's how I'm supposed to stand. Anyway, okay, so let's see how this corresponds to this again. How this is captured by this definition, right? What it's saying is that we're saying that the limit is 0, right? So what the definition says is that given any tolerance around 0, there's a time past which everybody is within that tolerance of 0, right? So given any tolerance of C, there's a time, we could choose this time, say, past which everybody satisfies the tolerance. Right? Everybody satisfies the tolerance. For example, if I said, I want all your outputs to stay within 1 or 0, well, what will you choose as your n? Go ahead, Victor. 1, right? 1. Because past 1, everybody stays within, past 1, right? Past 1, everybody stays within 1 of 0. Right? What if I said, I want you to stay within 1/100th of 0? What would you choose as your n? Go ahead, Mariah.
100.
100, right? You choose 100 because at that point your height is 100, and past that point everybody's less than 100th, right? So and you see that, well, no matter what epsilon you choose, right? If I choose an epsilon over here, what's going to be my n? Victor?
1 over epsilon.
1 over epsilon, right? 1 over epsilon will do it. Because at 1 over epsilon, your value is going to be epsilon. And past there, you're always going to be less than epsilon. Okay. So this is the game. Okay. Anyway, don't worry too much about it. But just try to link it back to the previous idea. Yeah, Mariah?
So like when we're doing lines,
Yeah.
it's just epsilon times the slope, but it seems to be the same thing here, right?
It's a very similar thing, yeah.
Okay.
Yeah.
Can you still use the slope to find x?
Can you still use the slope?
Never mind, that doesn't make sense.
There's no slope.
Yeah.
There is no slope.
There's something like 1 over x.
Yeah, yeah. This is no, you can't, as you see,
I see.
because there's no line.
Yes.
But there are some standard tricks. First, let me write it up. Right. If the limit of f of x is some number L as x approaches plus or minus infinity, then we say y equals alpha is a horizontal asymptote of f. Okay. So let me show you. A lot of the problems are going to use the following trick. Somebody says, here is a function. What's the limit as x goes to infinity or negative infinity? Okay. And the algebraic trick is this. You say, well, look, as x goes to infinity, I'm going to divide top and bottom by the highest power I see. Okay, so I'm going to divide top and bottom by x squared. So I get 1 plus 1 over x plus 1 over x squared on the top. On the bottom, I get 3 plus 2 over x squared. Right, so divide top and bottom by the same power. You can't divide them by different powers because that would change the function. Right? But you're certainly allowed to multiply by 1. So I'm going to multiply top and bottom. I'm going to multiply the thing by 1, this disguised 1 here. 1 over x squared over 1 over x squared. Okay? And then you say, well, as x goes to infinity, the top is going to go to 1 and the bottom goes to 3, and so I get 1 over 3.
Can you do that again?
Yeah. As x goes to infinity, what happens to the top? Well, 1 over x goes to 0. As x goes to infinity, 1 over x goes to 0. 1 over x squared goes to 0. And the 1 stays as is, as x goes to infinity, so you just get 1 on the top. Bottom, the 3 stays as is, the 2 over x squared vanishes. So you get 3.
What is that square root?
Well, as x goes to infinity, you're going to get 2 divided by increasingly large numbers. 2 over a billion, 2 over a trillion, squared, et cetera, et cetera. Okay. I should have commented earlier that we still have, 1 still has the same theorems for limits at infinity. Okay, so if the limit of the top and the limit of the bottom exists, then the limit of the quotient is going to be the limit of the top or the limit of the bottom. The same. We can still use that same sort of reasoning for these limits as we did for the old limits. Yeah, Megan.
How do you know to divide by x, like x squared?
You just look at the thing and look for the highest power and divide by the highest power. That's the trick. Yes, Kimaya.
Wait, so when you do that, when you divide by the highest power, just anytime you see the limit of the fraction?
If you have some rational function, you're wondering what happens as x goes to infinity. Right? It looks like you get infinity or infinity.
Yeah.
Right? But maybe it's not so.
So
Right?
you can divide.
You can multiply by 1. You multiply by 1, and you see in fact that they approach a fraction, and that fraction is 1/3.
Yeah.
Okay. And so intuitively, the idea is that, well, as x goes to infinity, these guys don't matter. The x and the 1 and the 2 don't really matter that much. Rather, the things that are going to be important are the things of highest power. Right? So you just ignore these guys and you say, oh, I get 1/3. Okay. That's the intuition, and then you can make it more precise by make it more rigorous by actually doing algebra to see it. Yeah.
Okay, so I actually remember learning this. So would it be mathematically incorrect to just kind of cross them out when you're doing columns?
It's not incorrect, but it's justified by this.
Okay.
It's justified
so
by
I was
this.
doing a problem and I
Yeah.
just cross them out. Okay.
I prefer that you actually show what you're doing, yeah, rather than just crossing it out. Okay, let me do one last example, which is slightly more sophisticated. Okay. So the limit as x goes to infinity of sine of 2x over 1 plus x squared. Okay. So here's one way to do it. Okay. You say, well, I'm going to play the same game. I'm going to divide, say, top and bottom by x squared. I'm going to divide top and bottom by x squared. And then I'm going to look at the limit of the top and the limit of the bottom. Right? The limit of the bottom is 1. Right? As x goes to infinity, this 1 over x squared goes to 0, the bottom goes to 1. What about the top? The limit of sine 2x over x squared. Well, what you can do is to use the pinching theorem. Say, this is smaller than 1. Sine is always smaller than 1. Right? Sine is always bigger than negative 1. So use the pinching theorem. Right? You can trap this between these two guys and let x go to infinity. Right? Take the limit as x goes to infinity. This will go to 0, and this goes to 0. And so this thing is going to go to 0, and so you get 0 over 1. So a slightly more sophisticated example, using the fact that we still have the theorems that we had before are still okay for limits at infinity. Yes?
Is it okay if we just take the exponent of x, and then multiply 2 by 2, and then use sine 2x upon 2x, and then you get 1 by x on top, and you get that tends to 0.
You're talking too fast for me. Come show me afterwards. I'm sorry. Come show me. Oh, you can show me right now. Okay. No, actually, I'm gonna. That's it for today. That's it for today. Come on up here.